So maybe what I'll do, since it's 12 after, is I'll just get started on my intro, and then we'll do an exercise at the end of that. If anyone needs help troubleshooting the installation, just let Jessie or I know. We can help you. Or Caleb know. Mm-hmm. I'm volunteering you to help with installation if needed. Yeah. Okay, so should we get started? You guys good? All right. Okay, so I'll spend a few minutes on this just to kind of set the stage a little bit and make sure that everyone's familiar with some basic concepts before we dive into some of the code stuff. Okay, so I was going to start with this question, which is, why would we want to use a quantum computer? There's quite a bit of hype around quantum computing, and some people think quantum computers will replace classical computers, that they can solve any problem faster, that they're some kind of really great all-purpose machine that you can just solve any problem with. In reality, you would only want to use a quantum computer for very specific kinds of problems where you can get a computational advantage. Because there's a lot of overhead associated with using quantum computers, and very often we already have efficient classical solutions. So here's kind of a little bit of an example to illustrate. So whether or not quantum computers are always faster. So if you wanted to ask, if you have two numbers, how long does it take to multiply them? We're pretty good at doing that classically already in a fraction of a second. If you wanted to do this with a quantum computer, given all the overhead, this would take many orders of magnitude longer to do. So you probably wouldn't want to perform basic multiplication tasks with a quantum computer. If you flip this around and you say, can I find the factors of a number? It turns out that classically this takes a really, really long time, but there is an efficient quantum algorithm that does this, which is Shor's algorithm. So this kind of illustrates that there are some problems where you would definitely not want to use a quantum computer, and there are some where you might want to. And this is a really overly simplified picture of kind of the complexity landscape of problems that we might want to address with quantum or classical computing. So in the middle, the white blob are problems that we can solve efficiently already with classical machines. The light blue outside of that are problems that we can't necessarily solve efficiently today with classical machines. And then this sort of elongated darker blue are problems where we think there are efficient classical solutions. So some examples of things that are in the this light blue category of things we can't adequately address today are things like factorizing large numbers and simulating quantum systems. But we know that there are efficient classical or quantum algorithms for those kind of problems. And then there are known examples where this dark blue oval extends out beyond the light blue. So that's kind of interesting as well. But this is, a lot of this hasn't been settled, and this is a very highly simplified picture. But just to show that, you don't want to throw a quantum computer at any problem. So there's, in the sort of complexity theory world, there's a name for the kind of problems that quantum computers can solve efficiently, which is BQP, or bounded error quantum polynomial time problems. There's a few problem types that live in that class. So solving large linear systems, maybe you've heard of the HHL algorithm, that has an efficient classical algorithm. Simulating quantum systems, so if you wanted to find the ground state of a molecule or simulate dynamics, and quantum walks, search problems, things like that. So also factorizing large numbers, discrete log problem, things like that. So these are the kinds of, at a very high level, problems where there are efficient quantum algorithms. So we might want to look for applications that are in these kind of buckets. Okay, so then the other part is if you're trying to think about when to use a quantum computer, sort of one of the first things you might want to start with is seeing if the problem has any sort of interesting structure to it that you could use quantum entanglement to represent. And this sort of boils down, like any sort of thing you want to do with a quantum computer boils down to the underlying quantum circuits that you're running. They have to be hard to simulate classically, because if they weren't, then you could just simulate them with a classical machine and solve the problem classically. So this is kind of the foundation of any sort of application or algorithm, is the circuits need to be hard to estimate classically, and that kind of gives you a necessary condition but not a sufficient condition for a quantum advantage. So what makes a circuit hard to simulate? I think there's not really a really simple answer to this, but there's a few things we do know, which is you need a lot of entanglement. You need to be able to create interference, and I'll talk a little bit about what that means. But essentially, you want to be able to create constructive and destructive interference of the amplitudes of your wave function. And then the circuit needs to be algebraically complicated. And what that means is there are known sets of gates called Clifford gates that if you built a circuit out of those gates, there are known classical algorithms that can simulate those efficiently. So just having a lot of entanglement or a lot of gates is not alone sufficient. You kind of need at least these three things. Then the other thing is if we wanted to run stuff on today's hardware, it's noisy. And so you want to kind of look at what are some short depth circuits that we can run on today's hardware that are still interesting and hard to simulate if you scale them up. And there's been some work showing that there do exist these kind of short depth circuits that are hard to simulate. So then, what kind of circuits are hard and how might you use them? There's a few kind of different ways of thinking about it. So one, on the left, I'm showing if you want to, you can create quantum circuits where if you wanted to classically sample from the distribution that was produced by that circuit, it would be hard to do that classically. And there's a category of quantum circuits called IQP where this is known to be the case. So if you, the distribution created by these circuits is hard to sample from classically. And those can be used in different kind of applications. There's, on the right-hand side, there's an example. It's called a forrelation circuit. It's connected to some more like theory stuff that I don't want to talk about here, but this circuit is conjectured to be hard to simulate classically if you scale it up. And so these are kind of two general types of circuits that you might encounter, but then you might be wanting to know, like, what can you do with these? Are they useful for anything? I think we're starting to answer these questions. So this example of the forrelation circuit, we do know a way to use this in a kind of meaningful way, which is in machine learning. So it turns out that forrelation circuit I showed you, it's actually a more general version of a circuit that you can use to calculate quantum kernels. So you can use that to, if you guys are familiar with kernel methods, you can use it to compute similarity measures between data. And so that circuit has a hard to simulate sort of condition, and it has some kind of practical application. And then let's see, last year, 2021, that paper was taken a step further, and it was shown that there's actually, there exists a case of this circuit that can provide a quantum advantage, but it's not very practically relevant in the sense that it's doing machine learning that you probably wouldn't want to, the problem it was solving was not particularly useful. And then there was work that was building on that was showing how to generalize that framework to data with group structure, which might have more practical, immediate practical applications. So that's one example of where these hard circuits can find their way into a meaningful application. Okay, and then so that was kind of my little motivation for why one might want to use a quantum computer. I was going to, since everyone here said pretty much they don't have too much familiarity with basic concepts, I was going to spend a few minutes going over some kind of fundamental things. And also, please stop me if you have any questions. This can be as interactive as you guys want it to be. All right, so, well, maybe I'll stop there. Do you guys have any questions so far? All good? Okay. All right, so I'm going to do a little sort of analogy, which is always kind of problematic, but I'll do it anyways. So like, in classical computing, we have bits, which are 0 and 1. They take on binary values. And we have logic circuits that are composed of gates. And these are sort of what together form the basis of classical computing. In the quantum world, we replace those things with quantum bits or qubits. And they can be represented by this sphere, which is called a block sphere. And the state of a qubit can live anywhere on or within the surface of the sphere. And essentially what that means is it can be a linear combination of the states 0 and 1. And then instead of classical logic circuits, we have quantum circuits, and they're also composed of gates and measurements, so gates and measurements. And together, these are what form the basis of quantum computing. All right, so I'm going to go through a few kind of basic ideas that we use, and then, but please stop me if you have any questions. So the first is this idea of superposition, which I kind of alluded to. So with quantum computing, we always talk about these basis vectors called 0 and 1, and they live in this two-dimensional complex vector space. You can write down any state in that vector space as a linear combination of 0 and 1. And in the quantum computing field, we usually refer to 0 and 1 as the computational basis, because that is the basis in which we can natively measure the qubits on the hardware. Then we also can perform measurements on quantum states. So I'm illustrating the block sphere here again, because what happens when you measure is you can think of, if you have a vector in this sphere, if you make a measurement, you can kind of think of it as like projecting, what is the projection of that vector along some axis? And that will give you the probability that you'll see an outcome 0 or 1. So if we measure this, can you guys see this cursor? Yeah. If you measure the state, you'll see the state 0 with probability A, absolute value A squared, and state 1 with probability absolute value B squared. And so that's kind of at a very basic level how we measure quantum states. Then there's also this idea of entanglement. So if you have more than one qubit, in general, you can write down a 2-qubit state like I'm showing here. So you have 4 complex amplitudes. And when at least 2 of these amplitudes are non-zero, you can get entanglement, but not necessarily. So let me give you an example. So the first state in purple, this is a linear combination of 2 2-qubit states, but it turns out that is not an entangled state because you can just pull out the first 0, and then you have the state 0 that's multiplying the linear combination of 0 and 1 for the other qubit. So those are in what's called a tensor product state, so they're not actually entangled. On the other hand, the 2 at the bottom in blue, there's no way that you can kind of pull those out or factorize them. So we would call those entangled. And what that means is if you were to measure the state of one of those entangled qubits, then you know the state of the other one right away. All right, and then this idea of circuits that I mentioned before, which is, and this is kind of the building block of the quantum algorithms and applications that we're running. So I'll kind of give you the anatomy of a circuit and how we think of these. So you have these different horizontal lines. Those represent the qubits. So we have a set of 4 qubits on the left. We initialize them to the 0 state or the ground state. And then we apply a sequence of gates running from left to right in time. So we have some single qubit gates in red and some entangling gates in blue. And at the end, we make a measurement on 1 or more qubits. And at the output of that, we get a bit string. And so you can write what is the probability that I see any given bit string if I make a measurement, and it's just the projection of your state onto that bit string, and then you square it. And so this is at a basic level, what is happening when you're running quantum algorithms. You're initializing qubits, you're applying a set of gates, and you're measuring things. The other thing that makes quantum computing interesting is that when you run these circuits, you would in principle get a bunch of different bit strings out at the end. But what you can do is, for certain algorithms, the combination of gates that you use let you suppress or enhance the probability of getting certain bit strings on the output. And what's nice about that is if you can do this in a clever way, then you can enhance the probability, shown here in red, of getting the correct answer. And so this is kind of what a lot of algorithms are doing. Like if you're familiar with Grover's search, that's what it's doing. It's kind of flipping amplitudes and amplifying them. And so at the end, if you measure, you should get the right answer with high probability. All right, any questions on that so far? Oh, any takers? Okay. All right, then there's two really important tasks that I want to cover, and these will show up again in Jessie's section when she talks about runtime and this idea of primitives. So if you kind of look across all of quantum algorithms and applications, there's in most cases two basic things that you're really doing. So one is sampling, which just means I'm going to prepare some qubits, I'm going to run a set of gates on them, and then I'm going to make a measurement and get a bit string out. And so that's called sampling. Like I'm trying to sample from the distribution created by that quantum circuit. There's some examples of where you would use this that you might be familiar with. So quantum phase estimation, if you're trying to estimate eigenvalues of a unitary operator, Grover's algorithm, recommendation systems, things like that. The other basic task is computing expectation values. So if you have some observable that you want to measure, maybe it's the energy of a system, you do that by computing expectation values of operators. And this is also very, very foundational. So algorithms like VQE, which you might have heard of, where you're wanting to minimize the energy of a quantum system, like find the ground state of a molecule, you would calculate expectation values there. If you want to compute quantum kernels, if you want to do combinatorial optimization, all that stuff requires these kind of basic tasks. And Qiskit Runtime, which Jessie will introduce and talk about in a little bit, it provides these two tasks as primitives. So it makes it available as kind of a nice function that you can use and kind of insert into your applications or algorithms and perform these basic tasks. Okay, and then I wanted to spend a few minutes on how do we calculate expectation values, because this will be part of the first exercise. So I'm going to give a very simple example for this slide, and then you guys will try to see if you can do the same thing but for a different operator. Okay, so the question is, if we have an operator, which is, actually, let me pause. Are you familiar with what the Pauli matrices are? Okay, maybe I should have had a slide on that. So the Pauli matrices are single qubit matrices or operators that we use to, they're single qubit gates that we can use to apply to qubits. So you can think of them as, if you remember that block sphere, if you have a vector in the block sphere that represents a qubit state, you can think of the Pauli matrices as like rotating the state of the qubit on the sphere. So it's a way of performing single qubit operations. So like, for example, the Pauli X gate is kind of like a bit flip. If the qubit is in the state 0, it flips it to the state 1 and vice versa. And so the Pauli matrices are really important. They show up like everywhere. And question?
What's the difference between a circuit and an operator, or a gate and an operator?
A gate and an operator. So they're kind of the same. A gate is a unitary operator, but we call it a gate because it's it's in a circuit, so it's like an analogy to classical logic gates in a classical circuit. Good question. Okay, so the question is, if we want to calculate expectation values, how do we actually do that on a quantum computer? And in this very simple example, we'll just take the poly Z matrix or operator, which is just a diagonal operator with diagonal entries 1 and -1. So if you apply that operator, it just does like a phase flip, essentially. So the expectation value, you can define it here. You have some wave function or some state psi, and you're trying to compute the expected value of the operator z. So you have the state on each side and the operator in the middle. Then what you can do is you can rewrite the operator z in terms of the computational basis, which are these 0 and 1 states. So this operator is a diagonal operator, and it has eigenvalues 1, which is the coefficient in front of the 0, and -1, which is the coefficient here. Then if you just plug this expression into the definition of expectation value, you get this set of equations over on the right-hand side. Okay, so we'll go through this one line at a time. So here we get, this is just plugging it in. I didn't do anything fancy. This term here, you can sort of play a trick and flip one of them around and add a little star on it, and you can write it as the projection of the state psi on the state 0, absolute value squared. And then you can do the same with the state 1. And it turns out these projections and the amplitude squared, these are just probabilities of measuring the state 0 and the state 1. So you're just projecting the state onto one of the computational basis states. And that's a probability that you can measure by sampling from the quantum computer. So what you would do to calculate this expectation value is you would initialize a qubit to the state 0. You would apply the poly Z matrix or poly Z gate, and then you would measure it a whole bunch of times, and you get a histogram of the probability of the counts of measuring 0 and 1. And that'll let you estimate probability of 0 and probability of 1. And then you just subtract those two. And that gives you the expectation value of poly Z in the state psi. Does that make sense? Should I go over any of that again? Because this will be your first exercise, so please ask questions if it's not clear. All right. These equations will be in the notebook that you guys will have access to as well, so you can look back at it again. But so then we can do that. We can play kind of the same tricks for the other poly operators. There's a little bit something extra that you have to put into it, but that'll be for you guys to figure out. I'll give you a hint, though, in the notebook. Okay, and then I wanted to give a quick preview for some of the things that Jessie will touch on and that I'll touch on in part 3, which is that, and I've kind of said this multiple times, which is these two tasks of sampling from quantum circuits and computing expectation values. These show up in like every application or algorithm for quantum computing. And one of the most well-known instances of this are called variational quantum algorithms. Maybe you guys have heard of them. One really kind of well-known one is kind of the workhorse of quantum computing, near-term quantum computing. It's called the variational quantum eigensolver. And people use it for computing ground states of molecular systems or things like that, like in chemistry or material science. There's also, if you want to do combinatorial optimization, there's an algorithm called QAOA. It's the same idea, though. You're computing expectation values of operators. And you can also, this shows up in machine learning in the context of kernel methods. So if you want to calculate kernel matrices for your data points, this is essentially an expectation value. Okay, sorry for the blinding white. So, okay, and then since you guys said you were not super familiar with Qiskit, this is just a high-level picture of the architecture of the stack. So at the bottom, let's start here. So here is what's called Qiskit Terra, and this is kind of the foundation of Qiskit. It lets you build basic quantum circuits, transpile things to hardware, kind of all like the sort of basic tasks that I was mentioning, sampling, expectation values, all that kind of stuff. Underneath here is Qiskit Air, which is a package for simulating classically the quantum circuits that you build. There's also some hardware that's down here that you can run the quantum circuits on instead of simulators. IBM provides a bunch of different backends. What's the largest number of qubits that we have available? 127 so far. And then here at the top left are the application modules. So there's Qiskit Nature, which is for chemistry, material science kind of problems. We have Qiskit Optimization, which is for solving combinatorial optimization problems like max cut, although don't expect quantum speedup. Qiskit Machine Learning, these kernel methods I mentioned are available through there, and then there's a finance package as well. And then on the right are some other kind of more like experimental list tools of sorts, if you're interested in that. And then I wanted to point out a few extra things in case you guys hadn't heard about it. So there's the Qiskit textbook, which is pretty great. It has a lot of really good kind of intro material, I think exercises too, that are built into the textbook. If you haven't looked at that, I would recommend checking it out. There's a bunch of other stuff too. There's a YouTube channel, there's Medium posts, lots and lots of stuff, so if you're interested. And then also plug this. I think the registration is already over for this, but maybe for next summer, if you guys are interested, there are summer schools. So last summer was machine learning, and then this summer is, what is the summer? Quantum simulation. So these are really cool. I participated in one last summer, and it was pretty fun, so you guys can check that out if you want. Okay, questions before we move to the exercise? Anyone need help with the installation? Are you guys all good?
I missed that in the meeting. Is there a website?
Oh, yes. Here, let me go back to the beginning.
Hopefully you can clone it. I was trying to clone the repo on the Wi-Fi and it timed out, so. Is there like
Go here.
anything here? Is it a
Follow her link in the description. I don't think she has the Git, but it's the different protocols. It's HTTPS, not the Git one.
Gotcha. Yeah, I went to the repo and I just cloned it using SSH.
Oh, we did?
You were able to do it here?
I timed out first because
Gotcha. Oh, I see what you mean. Gotcha.
there's a different different ways or protocols of doing it.
Are your slides in the repo?
They are not. Apologies. I'll probably.
Something we would like to do?
Yeah, I think I can post them there. Yeah, I'll see it if I can do it a little later. I think Jessie's slides should be in there.
Yeah, use the HTTPS link, not the SSH link.
Okay.
The trouble I'm having is finding credentials. I've got the API token, but I don't have some of the other ones.
Oh, for the IBM Quantum account?
Yes.
Do you want to help?
So you should have the HTML code, right?
I've got the API token. It looks like I'm supposed to have other pieces of information.
You just need the API.
That's all I need? Okay.
And this is the file name of the exercise for part 1. It should be in the tutorial or docs/tutorial folder. So, and then I can actually go through some of that. How am I on time, Jessie? Okay? Okay. Did everyone find that notebook? Good, okay. All right, so I was going to walk through some of this in the notebook itself, and then inside of this notebook, there's 2 places where there's exercises that you guys can try. But let me go through this first. So I was going to show using Qiskit how to do these 2 tasks, sampling and expectation values, in a very basic way. There's better ways to do it that are in Qiskit itself, but I'm just going to show you a sort of manual way to do it. Okay, so first, sampling from quantum circuits. All right, so since you guys were not too familiar with Qiskit, I'll kind of show you some of this like basic stuff, which is, so from Qiskit, we want a few things. We want a quantum circuit, which is this object here, and this is what we use to build these circuit diagrams that I was showing you. So we can add gates to them and build circuit objects and then measure from them. We're going to use basic air, which is the classical simulator that comes as part of Qiskit Terra when you install it, or Qiskit. And then a transpile class, which lets us take any given quantum circuit and map it, so to speak, to the topology of the quantum hardware that we're running it on. Jessie can talk more about what that means in practice. Okay, so what we first start with is defining a quantum circuit, and here we're just telling it that we want 1 qubit. Is this big enough, by the way? Can you guys read that text? Yeah. So we want 1 qubit in the quantum circuit, and then the second line here just means I'm going to add a poly X gate to that qubit, and then I'm going to measure. I'm saying measure all, but there's only 1 qubit, but I'm going to add a measurement to the end of the circuit. And so when you run this, it looks, you see this kind of diagram here where this horizontal line is the qubit, and I put an X gate on it. And then at the bottom is like a classical register, kind of, where I am measuring with this little M symbol, and then the output of that measurement, which is either 0 or 1, is stored in the classical register. So once we've defined a circuit, then we want to tell Qiskit where to run the circuit, which means picking a backend. And the backend can either be a simulator, which is just classical, or a real quantum machine. So here I'm going to use a simulator that's called Chasm Simulator. And what this does is it kind of mimics what you actually do on hardware, where you sample from a circuit and you get a distribution at the end. And so as part of that, we specify the number of shots, and shots is just the number of times I sample the circuit. I run the circuit, I measure it, and I repeat that shots number of times. And then, so once I have my backend, I can call the run method, and I pass it the circuit, and the number of shots I want to sample, and then I can get the result out of that. So the results object contains a bunch of stuff, but what we care about are the counts. So we get this counts dictionary from the results, and I'm printing it here, so it just has 1 entry, which is good, because that's what you would expect in this case. So what I did is I started a qubit in the ground state, which is the 0 state, and then I applied an X gate, which just is a bit flip. So it goes from 0 to 1, and when I measure, I should only see 1, because that's all that it did. There's no superposition or anything like that. So I should only see 1. And indeed, in the dictionary, I get, I observe the state 1, and I see it 8,192 times. And that's just the number of shots that I measured the circuit with. And so if you look at this dictionary, you can say, okay, what was the probability I measured 0? And it's 0, because there's no entry in the dictionary. And then the probability to see 1 is 100%. So that is all good. Then if we wanted to create a superposition, we can use lots of different quantum gates for that, but here we'll use what's called a Hadamard gate. And the Hadamard gate, if you initialize the qubit to the 0 state or the ground state and you apply Hadamard, what it does is it creates an equal superposition of 0 and 1. And so if we apply the Hadamard gate here and then measure, we get the following circuit. So it looks the same, except I'm replacing X with H. If I do the same thing as before, I pass to the back end the circuits. I get the results, the counts dictionary out of it. And if I look here at the output, I get the state 1 and the state 0 with roughly equal probability. And the reason why they're not exactly the same is because we're sampling the circuit a finite number of times. So there's a little bit of sampling noise there, finite sampling noise. But they're roughly equal, which is what you would expect for this gate. Okay, and then I'll just show you this quickly, but you guys can come back to it. This is the exercise. So first part of the exercise would be kind of repeating what I just showed you, but use a combination of single qubit and 2 qubit entangling gates. And there's a circuit library that you can kind of decide which ones you want to use. 2 suggestions, you can do whatever you want, but 2 suggestions is building a Bell state or a GHZ state. Those are pretty simple and interesting. And so just do the same thing, build the circuit for that, measure them, run it with the CHASM simulator, and then plot a histogram of the output and see if it is what you would think it should be. Okay, so we'll come back to that in a second, but the second part is this expectation values. So this is the same stuff I showed you on the slide for how to calculate the expectation value of the poly Z operator. So you guys can look back at this if you want, but essentially what you do is you create a circuit that represents the state of interest psi that you care about, and then you sample from it a bunch of times. You get the probability to see the 0 state, the probability to see the 1 state, and you subtract them. And that gives you the expectation value of this operator with respect to this wave function or the state. So to do that in Qiskit, I'll show you. Let's suppose we want to calculate the expectation value of poly Z in the state 1. So this is, so all I'm going to do here is just define essentially an array that represents this state 1. So it has 2 entries, 0 and 1. This is the computational basis state 1 that we already saw. And I want to calculate, with respect to this state, what is the expectation value of the operator Z. Let me zoom in a little for you. Okay, so what we first do is we initialize a quantum circuit to the state 1, because that's the state that we're interested in. And there's kind of this nifty thing in Qiskit where you can use this initialize method and pass it a list of amplitudes, and it will prepare that state for you. So it's kind of a nice little shortcut. And then we want to measure this circuit because we're interested in the probability of 0 and 1. So we do the same thing I showed you in the first part with sampling. You pick a back end, you pass it the circuits, you get the counts dictionary. And here our dictionary only contains 1 entry, which we'd expect because we're initializing it just to the state 1, so we only see the answer 1. And if we take these 2 probabilities that we get from the counts dictionary and we subtract them, which is what I'm doing here, then that should give us the expectation value of this operator. And the answer we get is -1. And the reason why that makes sense is because the state 1 is one of the eigenstates of this operator Z. And the eigenvalue associated to that eigenvector is -1. So this is exactly what we'd expect. Okay, then I'll go through this a little quickly. So this is a similar thing. I'll go through this kind of fast in the interest of time, but if you wanted to do the same exact thing, but you wanted to ask now what's the expectation value with respect to the state plus, and the state plus is just the equal superposition of the 0 state and the 1 state. So it's 1 over square root 2, 0 plus 1. So we can define that state as an array again. We can initialize a quantum circuit for that state using this initialize method. We measure it, and then we will pass it to a backend and get the counts dictionary again. And here we see that we get 0 and 1 with equal probability. So now if I was to subtract these two probabilities, I would get roughly 0 for the expectation value. And that makes sense because the plus state is, it turns out it's, you can write it as like an equal combination of the 0 and the 1 state. And so the two, like the expectation value for that operator then just like exactly vanishes in that case. If you think of the block sphere, with 3 axes, the plus state is the plus x direction, and you're asking what's the expectation value of the z operator, which has eigenstates pointing straight up and straight down. So that it kind of makes sense, it's halfway between it, that expectation value should vanish. Okay, this is what I kind of just said. So the reason why you can do this is because when we measure quantum circuits on the hardware, we natively measure in the computational basis state, which is the eigenbasis of the Pauli Z operator. And so if you wanted to measure a different operator that doesn't have that eigenbasis, there's kind of a little something that you have to do that. So yeah, this is just this is the block sphere that I was kind of just mentioning. So this is one of the eigenvectors of the Pauli Z operator. And then I think, yeah, so the exercise of the second part, time willing, is to try to do the same thing that I showed here, but for Pauli X and Pauli Y operators. And the hint is that you can write the Pauli X operator in terms of the Pauli Z, but with kind of a change of basis using the Hadamard gate. And you can do the same thing for the Pauli Y operator, but with this S gate and the Hadamard gate. And so if you were to work out the math for that expectation value I showed and plug in these kind of transformations, what you should see is that to measure those two operators, X and Y, you have to perform what's called a post-rotation to the circuit before you measure. So that's kind of the hint there. Okay, so I think that's where I was going to stop. How much time do we have?
We have time.
Yeah? So I guess if you guys want to take a crack at this for a few minutes, please ask questions. And then I think we'll have a 10-minute break also before Jessie starts. So should we say, how long should we say for this? 45, maybe is the bottom of the hour too long? 9:30?
9:30 is fine.
Should we say break at 9:30 and then come back after a few minutes? Good? All right. I will leave you guys this this again too if you want to look at it. As kind of a hint for the exercise. Okay. You have to do this transpile thing that I was mentioning. So the backend doesn't automatically recognize the Hadamard gate. So you have to transpile it to the basis set that it knows. So if you look at, let's see, where do I show this? Here. So see how I'm taking the circuit and I have to transpile first to the back end, and then I can pass it to the run method.
Oh, okay.
So it takes the Hadamard and it kind of rewrites it in a way that it understands, and then it runs it. Sure. I'll leave this up. I might go get more coffee. Yeah.
Oh, actually, go out during my session. Glick.
This one? No internet. UT. Looking for, like, so here, Qiskit Circuit Library. They have this, which is like the standard gates that they list, but to actually apply them to the quantum circuit, you don't have to do it like this. Like you can say quantum circuit dot X, right? Like, so where do they show that? Like those forms, you know what I mean?
Yes, I know what you mean.
Is it in the quantum circuit class, maybe?
It's not in quantum circuit. Some of the standard ones are in quantum circuit class.
Okay.
But the custom ones, they are in the gates definition.
In the what? Oh, it kind of shows it here, right? Like,
I know
It's
a bunch
just-
of them are there. I don't know if all
Yeah.
of them are there. I think, I mean, I know where they are in the source code. I don't know where they are in the API code.
yeah. So what are you looking at?
No, I was just looking to see if
Okay.
it's in the API doc.
Okay, so one thing you could look at is if you look in the Qiskit docs for the quantum circuit class here. This is, probably should be a better place where this is listed, but there's you can look at its list of methods and it will show you some of these will be the gates that you can add. Some of them are other methods. So for example, zoom in here. Like here's the C0 gate. So you would say like quantum circuit dot C0. Yeah, I think you can do either one. CX and C0 are the same. Let's see if they have that here. Yeah. Oh, here's some better ones. So this is the format that you can use to call it the method of the quantum circuit object. The link that I had in the notebook, you can use that too, but it's a little bit less obvious how to go from those to applying them as gates to the circuit. This is a little bit more intuitive. So maybe just look at these methods and see if you want to, like anywhere it says apply a gate here. Like for example, this CX right here. This applies this object capital CX gate, but you can just call the method lowercase cx on the quantum circuit object instead, and it's a little easier. Okay, so I'll just do the expectation value one, since that's probably the slightly more interesting one. So, ooh, can you guys read that? It's a little small. Okay, so I'll just show you the one for the poly X gate, and the one for poly Y is kind of the same. But so what you do is a little bigger. So if you think about this transformation that I wrote here, I'm trying to highlight, but it won't highlight. You can rewrite if you do a change of basis. You can transform the poly X gate into the poly Z gate according to this. And so what you can do is just go back to the original math that I showed you for computing expectation values, which I kind of repeat here, and just plug in, we want to calculate expectation value of X, but let's plug in that transformation between X and Z instead. And so you get this expression, and then you kind of play the same trick where you say the poly Z operator, I can write it in terms of the computational basis state 0 minus 1. And so then you get these two terms here on the middle line. And then you can rewrite these kind of two symmetric expressions in terms of just one with the amplitude squared, absolute value squared on the bottom line. And so what you can see is that to measure X, what you do is you initialize the circuit for psi, and then you apply a post-rotation, which is the Hadamard gate, to that circuit, and then you just do exactly what you did for the poly Z operator. You measure it a bunch of times, you get the probability to see 0 and 1, and then you subtract them. So it's the same exact process, you just have to figure out what is the right post-rotation to transform your operator into a diagonal operator, essentially. And this is all because we can only measure in the computational basis, which is the eigenbasis of the Z operator. So the tricks really, for measuring any operators, is just to figure out what's the right post-rotations. And Qiskit will handle this all for you normally. I'm just kind of showing you how to do it explicitly here. But there are built-in things for doing expectation values, and then the estimator that Jessie will show you handles this all automatically. So it's similar for poly Y. You do the same trick. You plug in this change of basis transformation, work it out, and in this case you would apply the post rotation, which is S dagger followed by H, and then you measure, subtract the probabilities, and you get the expectation value. So I kind of go through how to set this up with Qiskit here. Maybe we'll look at one of them. So let's say I wanted to measure expectation value of X in the 1 state. So the 1 state on the block sphere is the one that's pointing directly down. And we want to calculate the expectation value of an operator whose eigenbasis is on the plus and minus X axes. So it's kind of like halfway between the computational basis state of 1 and 0. So you might, just looking at this, expect that the answer should be 0. And if you prepare the state 1, and then you run this here's where I do the post-rotation. So you initialize the state 1, which is the state that we're doing the expectation value in. And then this is where we apply a post-rotation. So that's all you do, is you just apply a Hadamard, and then you measure and rinse and repeat. And so what we get is that the expectation value is approximately 0. And you can kind of explicitly work that out with the math, and you'll see that you end up subtracting 1/2 from 1/2, which is 0. And then you can do the same thing for all the other states, plus the plus state, and then for the Y operator. But yeah, at the end of the day, you just have to figure out what the right post-rotation is, and that's pretty much it. Shall we go on a break? Yeah? Coffee?
Are you going to post these in the...
Oh, yes. So that if you look at, if you go to the solutions branch here, it's in the same directory as the tutorials, but just with the little solution tag appended, or word appended to the file. So no peeking at the other ones yet. All right. I'm just going to unplug this for a little bit. Yeah. Should we do a 5-minute break? So come back at 9:38.
do your cursor? My cursor is just gone.
I see it. It's okay.
Oh, you see it? Oh, okay.
I think.
No, because I wanted to do this. I guess it doesn't work. Oh, it does work. Just found out we can do laser pointer. But it doesn't show on the screen. It's really annoying. Like, I can't see. Yeah, like I have to look at this. I have to look at this big screen.
Maybe, yeah.
Yeah. Oh well.
If you could mirror this somehow, but it's getting too fancy for me.
It's been a long time since I had to use a real projector. Usually it's just WebEx. Yeah.
This Colorado thing's serious. Did you see the schedule?
What?
This Colorado thing's serious. Are you aware of that? Jessie?
Which one?
There's a Colorado quantum thing. Starts on Sunday, that's pushing. Wait, what's going on, Bart? I'm mad. What is this?
IEEE services, they also have a home software track, and they, apparently somebody signed me up for as a co-chair, so I got to go, but it's the same way, it's like right now.
Oh.
And I have already set up.
You shot yourself in the foot. That's sad.
I know, so sad. Are you guys going?
It was.
And he's actually gonna be talking about, not just Qiskit Runtime, so he's gonna talk about the real-time computing stuff. Yeah, I can totally talk about it.
I need to get my passport renewed just in case I have some opportunity to go somewhere awesome.
All right, let's get started. So I will be talking about part 2 of this workshop, which is about Qiskit Runtime. But before I jump into Qiskit Runtime, I want to first talk about variational quantum algorithms. These are a type of algorithms that use a classical optimizer, such as the ones you would find in SciPy, to train a parameterized quantum circuit to approximate the solution of a given problem. And normally you would run your circuits, calculate the expectation values, plug these expectation values into the optimizer, get a new value back, and that's how then you would use that as the parameter for your next set of circuits. So VQAs are very popular today because they typically use fewer gates and qubits, and therefore they are more suitable they're more resistant to noise, and today's quantum computers are quite noisy. Well, I guess I already said that, so they're suitable for near-term quantum computers. I feel like I jump ahead of myself, but VQAs are typically iterative. You start with a parameterized circuit, and I will go more into that later. You run your circuit, you get the output, such as your expectation values, and then you put that into a classical optimizer. Then the value from that optimizer will then be used to generate the next set of inputs into your parameterized circuit. So what does this have to do with Qiskit Runtime? VQAs are very popular, especially in recent years because they are typically higher level algorithms that people use to solve like chemistry or machine learning problems. They're higher level, so a lot of people don't have to play with gates and qubits. That's why they're popular. And before Qiskit Runtime, typically when you run a VQA, let me see if I can find the laser thing. So here's your laptop. You start with your parameterized circuits, and then you send your circuit into some kind of remote quantum computer. Or well, unless you are based in a lab, otherwise you are probably gonna send your job to a remote quantum computer. And because quantum computers are still very scarce and expensive resources, typically there is a queue. You have to wait your turn before your circuits will get run. So once it gets run, you get the output back, which get fed all the way back to your laptop, gets fed into a classical optimizer, which updates your next set of circuits. And then you have to go to the queue again, send your circuits to some remote QPU that can take a long time. So this whole loop is quite inefficient because for every execution, you have to go through the queue and go to the remote. You have to send all your data over and go through the queue and go through the remote quantum processor. So, and that was the main reason that we introduced Qiskit Runtime. So Qiskit Runtime is a quantum computing service and programming model that would efficiently execute the workloads at scale. There are two parts of Qiskit Runtime. One is what we call Qiskit Runtime session. And this is similar to the classical session where you open a session with some kind of remote server, and then you can do interactive processing with that remote server without having to go through the queue, and you can also cache data on the server side. So that's basically what the runtime session, the idea of the runtime session is. And the second part of Qiskit Runtime is what we call the primitives. As Jim mentioned earlier, there are two basic tasks that a lot of people do, which is sampling the distribution as well as calculating the expectation values. And of course, it will be annoying having to do that by hand every time, and that's why we have these primitives. So let me talk a little bit more about Qiskit Runtime session. So the goal of it is to provide an interactive communication that would minimize artificial latencies. So it accomplishes that with a number of steps. One is that so once your session is open, every time you send your circuits in, those circuits are prioritized by the scheduler, so you don't have to wait in the queue for others to run. Another is data that's used within the session, such as these parameterized circuits, is cached on the server. And also that's, I will also talk a little bit more about this, is the transpilation can also only happen just once, so you don't have to do transpilation every time. And the third point is that the classical cloud technology has advanced quite a bit, and there is the serverless technology where you can upload your program into a cloud, and that can very easily scale the classical capabilities and use special hardware, such as if you want to use the GPU to do your optimization. And Qiskit Runtime makes it easier to do it. So the primitives are pre-built programs that gives you an interface to perform those basic quantum computing tasks. And much like the other cloud-based services you enjoy today, such as your Gmail or your Google Doc, because they are based in the cloud, there can be enhancements done to these programs that require zero interaction on your part. You write your program, and then if there are any kind of updates, you just get the benefit of it. And some of the updates can be such as any advancement in readout error mitigation. Oh, so what are the primitives? Today we have two. The first one is called sampler, and as the name implies, it samples the distribution of your circuit outputs. And it's useful for search algorithms like Grover's. And we also have estimator, which estimates the expectation values. It takes circuits and observables as inputs. And it's typically used in chemistry simulation, like in VQE or cause optimization problems. All right, and that's all the slides I have. Now if I can just figure out a way to switch. Oh, that is not the one I want. So,
Is this
sure.
one of the notebooks on the repo?
This is one of the notebooks on the repo. It is the Qiskit Runtime exercise. It's called exercise, but it also has the introduction part. Thank you. So the first, because we will be using resources on IBM Quantum, you do need to sign up for an account. Does anyone not have an account yet? Oh, well. So it's just, you can sign up for an account at the quantum-computing.ibm.com. And so here's my account, and let me just show real quick. So to find your API token, which is what we need, it's there's this little person icon, and there is account settings. And this is where you can copy your API token. All right. So because we are using a remote resource, the first step is to authenticate with the server. And the way to do that from Qiskit is first you need to import the Qiskit Runtime service. So it's from Qiskit underscore IBM Runtime import Qiskit Runtime service. And typically, if it's your personal laptop, I would just save the API token so I don't have to copy and paste it every time. So there is a save account option that you can use. And the channel here is because Qiskit Runtime started out on the IBM Quantum website. It's also available on IBM Cloud now. So you know if you are using an IBM Cloud account, then your channel will be IBM Cloud. If you're just using the IBM Quantum, which is what I posted here because it's easier to sign up than IBM Cloud, then that's the IBM Quantum channel. And if you have previously saved, so in the future, after you've saved it, you can just do initialize it with and specify your channel. And if you only have one channel, you don't even have to specify the channel. I'll just find it. But if you have not saved your account on disk, your API token on disk, then you specify the channel and you specify the token. Oh. All right. So here I'm going to, now that we've authenticated, I'm going to show you an example of calling the sampler primitive inside a runtime session. So there are a few steps involved in this. The first is to prepare the initial input data, and this is typically your parameterized circuit. And then you have to select a quantum computer to run on, what we call the backend. Then you can open a session and then submit your request. So the first step is preparing a quantum input. The sampler program takes a number of inputs. So the circuit is your quantum circuit. It can be parameterized or not. And if it is parameterized, then you can specify the parameters you want to use. You can choose to skip transpilation. I will talk about a little bit more about transpilation in a minute. But typically, if normally we would just let the program do transpilation for us. But if there are specific thing you want to do, like if you are studying, different transpilation methods, then maybe you can say, okay, I want to try different things. Then you would just say, oh, don't do it for me, I'll do it. So service is the service instance that we just initialized in our previous step. And there are other options like the number of shots. And usually we run a large number of shots because the quantum computers today are noisy. So each shot is basically a repeat of the same circuit, the execution of the same circuit. So you want to run a large number just so you can get a more accurate result. You can also find the inputs and outputs of these primitives on the website. So, so on the quantumcomputing.ibm.com, there is the programs, and under programs, you can see the sampler and the estimator. I probably should delete all these, but these are my own programs that I wrote for different things. Let's see if it'll load. I guess networking is a little bit slow today. Oh, there we go. So, it shows you all the inputs and all the return values. And it also tells you, when was the last time it was updated. Let's see. So, step 1, prepare parameterized circuits. Oh, I promised to talk about transpilation. So what transpilation, so transpilation is a term defined in Qiskit, and that is the process of rewriting a given input circuit to a different circuit. And why does it need to do that? A number of reasons. First is to convert high-level gates to basis gates. So kind of similar to classical computers where you write higher-level functions and the compiler just converts that to lower-level stuff. That in the quantum computers tend to have a small number of basis gates. Such like the Hadamard gate, for example, it is typically not a basis gate. It's a higher level gate. And the transpiler will convert that into one of the basis gates for you. Another thing is to map the input circuits to match the topology of a quantum device. So let me just, I think one of these is, no. So let me just show you one of the devices. So here is one of our real quantum machine. So this is what we call a coupling map, and that is the layout of the qubits. So this is a 5-qubit machine, and qubit 0 is connected to 1, 1 is connected to 0 and 2, and so on and so forth. But if you are trying to write a 2-qubit gate, like the CNOT gate we talked about earlier, the 2 qubits that you want to entangle, they have to be right next to each other. So there has to be connectivity among them. But when you are writing your circuit, it's already difficult enough. You don't want to have to look at the map and figure out which qubits are connected with which, and then figure out if you can apply those gates. So what we normally do is Qiskit would present to you as if all qubits are connected with each other. So you can write a CNOT gate between 0 and 4, for example, even though they're not connected. And the transpiler will just insert what's called swap gate to make sure that, so that to make change your circuit enough so that the 0 and you can do entanglement on 0 and 4. So that's another big piece of the transpiler. And the last thing is, just like classical compiler, it does optimization of your circuits for execution. Now you may ask, why is it called a transpiler and not a compiler if it does a lot of things as a classical compiler? And the reason being, we actually have another compilation process, which is take your logical, your high-level representation of a quantum circuit, your qubits and your gates, and actually translate that into something our control electronics would understand. So the way, sorry if this is too much tourist information, but I find it fascinating. So the way we control our qubits is we have a bunch of microwave pulse generators. So they generate microwave pulses and to stimulate the qubits. And so your circuit, your gates need to be compiled into something these waveform generators can understand. And that's what we call the compilation step. So back to our regularly scheduled topic, parameterized circuits. So transpiler, it makes things a lot easier for developers, so you don't have to worry about basis gates and coupling map, but it can be time consuming, especially if you are trying to do a lot of optimization. And with variational quantum algorithms, typically the circuit layout doesn't change. What changes is the parameter values. So for example, your circuit can do like an RZ gate, but it's really the rotation angle that changes. It's still the same gates. So we have this notion of parameterized circuit, which means you can create a circuit with parameters not yet defined, you can transpile this circuit once and then just bind it with different parameter for different execution. So this is an example of creating a parameterized circuit. And so Qiskit has a library of commonly used circuits. And here I just randomly grab one called real amplitudes. And you can go to the Qiskit documentation for all these circuits and their descriptions. So here I just say I want to use 2 qubits and I want the repetition to be 2. And of course I want to measure all my qubits. And this is a parameterized circuit with 6 parameters. And you can see here it had this 6 RY gates, and each one has its own parameter. And these parameters are undefined right now because I haven't really given it any values yet. All right, finally step 2, selecting a backend. So I kind of showed you a little bit that this is the page, the quantum compute resources is the page where you can find all the backends. And it gives you a lot of information about these backends. Can I go back to, oh, by the way, so all our backends are named after cities, but they are not in said cities. They are only in New York. Otherwise, we would have way more traveling opportunities. So yeah, Manila is not actually Manila, it's in New York. So this page tells you like it's a 5-qubit circuit. It's online. It has 12 jobs waiting to run. And more importantly, it tells you like the average CNOT errors or the readout error. And T1, T2, a bunch of values. Let's see. So you can look at that page to find a backend you want to run on, or you can do it programmatically. So one major selection criteria a lot of people use is to find the least busy backend, because these are shared resources. So sometimes the queue can be really long. When I say really long, like you can wait days before your job would run. So least speed is one of the common criteria. And then you can say you don't want any simulators, you just want real devices, and you want at least 5 qubits. So. And the API doc will tell you about the more different selections, but here is just an example. And then you can say, so each backend has 2 major methods that would provide information about the backend, the configuration and the properties. The configuration contains static information about the backend, such as the number of qubits. And the properties is the dynamic information about the backend, such as its error rates or the T1, T2 values. In this workshop, we will be using the simulator because otherwise we would have to wait quite a while for everyone's jobs to finish. So the simulator is the same simulator you just use locally. But this is a cloud-based simulator. And the reason to use a cloud-based is so that it doesn't lock up your CPU or eat your CPU resources while you're running your job. All right, so step 3, opening a session. Opening a session with one of the primitives is relatively easy. So here in this example, I'm using the sampler. So I just import the sampler class. And the typical way of opening a session is to use a context manager in Python. So here I can say with sampler, and then I pass in the parameterized quantum circuit that I prepared earlier. I have to give them the service which contains my credential, the backend I want to use, and it would return me a sampler object. I'm not doing anything in this session because I just first want to show how you open the session. So now I want to actually submit requests to this session. So this is the same syntax as before, where I open the session, give it my circuits and my selection of backend. And I can say, oh, now I'm ready to call the sampler primitive using the first circuit that I provided. And these are the parameter values that I want to pass to my parameterized circuit. And of course, I can print the results. So because this is simpler, it gives me a distribution of the measurements. So, the different probabilities of measuring 1, 0, 0, 0, 1, 1, and 0, 1. Oh, let me pause for a minute. Does anyone have any question? Sure.
Your sampler context with sampler and you pass in your service, you said something about a session. Does it open a session?
Yes, when you do a with sampler context manager, it opens a session for you.
So I was wondering, with the free account, how much of this can we access?
Oh, you can do all of the you can do all of the code. It just so the free account restricts the quantum computers you can use. So I think you can only do 5 qubits. Is the biggest that you can do. There used to be a 16 qubit, but I think they took that away.
I'm seeing just by logging in, it says I have access to the following systems. Some of them have 7.
Oh, I guess
thought
7.
7.
Okay, sorry. Yeah.
Yeah, 7 I think is.
I haven't used my free account in a long time, so I don't actually remember. But yeah, so yeah, I guess 7 is the largest that you can use. All right. Any other questions?
You can use the simulators for large sizes, right?
Yeah, so the simulator will simulate up to 32 qubits right now.
I also see one with 5,000, but it says simulator stabilizer, so I'm assuming that's not something we should be running on.
It is a simulator, but it's maybe Jin can talk more, but it's a no, maybe not. So it uses a different simulation method. So it's not a general purpose simulator. It would only take a certain type of circuits, and I cannot tell you which type of circuit because I'm not an expert in simulation.
You should be able to use like the chasm simulator that Jessie was
Yeah.
using, like all of that.
So
With a free account, you can run
me see
more than a 7-qubit circuit with that chasm simulator, right? Up to
right.
32, you said?
So the IBM Chasm simulator is a all-purpose simulator. So it would take any kind of circuit that you're passing, and it simulates up to 32 qubits. Okay. Any other questions? All right. So I'm now going to show you an example of submitting multiple requests. Because, well, let me first show. So I'm preparing another parameterized circuit. Again, I just pick a random one from the circuit library. And this one is called efficient U2. It has 8 parameters. This is probably a little bit hard to read, but just ignore the output. So as I mentioned, the whole point of having a session is that you can submit different circuits and different parameters within a session without having to wait for the queue. So here, I said I want to cache these 2 circuits, PQC and PQC2. Probably should have named them PQC1 and 2. So these are going to be transpiled and cached on the server side. So I don't have to send them these 2 every time, and I don't have to retranspile them every time. And then I can say, oh, I want to, use the first circuit on the list, which is PQC, and I want to use these parameter values. And I can also say I want to run 2,000 shots instead of the default of 1024. And similarly, I can say, oh, now my second request within the same session, I want to call the PQC, the first circuit, twice, but with different parameter values. And the third example is I want to use the circuits 0 and 1, so PQC and PQC2, and here are the values, parameter values I want to use for them. So this is how you can, open a session with a number of different parameter circuits, and then just repeatedly call the sampler with the same circuits, but different parameter values.
Is there a limit to how many calls
There is a time limit, and that is a very long time. I want to say 4 or 5 hours. There is documentation on Qiskit IBM Qiskit IBM Runtime that will tell you what the time limit is. So next I want to show, because we talk about how variational quantum algorithms tend to be iterative, so I want to show an example of an iterative processing. It is a bit of a contrived example, but I wanted to keep it small. So in this example, I'm going to prepare a parameterized circuit that only takes one parameter. And this parameter would determine the degree of rotation around the x-axis. So it will be somewhere between straight up or straight down. And starting from a quarter pi, we would increment the value of theta by the probability of getting a 1 from the previous job times pi. So for example, if I run a simpler job, I get back the probability of getting a 1 is 0.35, then the parameter to my next job will be 0.35 times pi. And this iteration loop would end when the probability of getting a 1 reaches greater or equal to 50%. So just a bit of a visual demonstration. This is a block sphere. So we start with the 0 state, and here is the x-axis that I want to rotate from. So I basically just kind of like going this way, rotate around x-axis until I hit the probability of getting, well, I guess you can't really see 1 here, the bottom is 1. Hit the probability of getting a 1 becomes greater or equal to 50%. So this is my little sample program. So again, step 1 is to create a parameterized circuit. And here, well, Qiskit circuit library doesn't have a predefined one qubit circuit, so I have to create my own. So I define my parameter. I create this 1 qubit circuit, and I said I want to do an Rx, which just rotates around the x-axis, with my parameter value theta for qubit 0. And I want to do my measurement. And this is what my circuit looks like. So then here my little program, or called iterative processing, I start out with my parameter value being a quarter pi. Then I open my simpler session, give it the circuit that I just built, and the backend, which we're just using the simulator. And I can call simpler with my circuits and my parameter value. And because, well, I guess I was kind of lazy when I did this, I only did 100 shots. So here is my my loop, my while loop, saying if the distribution of getting, the probability of getting a 1 is less than 0.5, so 50%, I'm going to continue calling simpler with a newly updated value. So here my value would be, getting the percentage of getting a 1. Just in case I get a 0%, which means this will become an infinite loop, so I give it a default value. So whatever percentage of getting a 1 is, I'm going to times pi and then add it to my theta value. So you can just see, and once I reach greater than 50%, then I exit my loop. So it's just a little demonstration of how you would take the results of a previous execution and plug it into your next one. All right, now is the exercise time. Before I go into the exercise, any questions? All right, so the exercise is to do basically what I just showed you, except with the estimator program. So you would open a Qiskit Runtime session with the estimator context manager. And then you can make multiple requests to the estimator primitive within the session. And ideally, the parameter value of the request would be based on the output of a previous one, and the loop has to end at some point. when some set target is achieved. So there is a link to the estimator API, and there is also a tutorial on the estimator. Estimator is slightly more involved than simpler because it takes more parameters than simpler, but the idea is pretty much similar. So how are we doing on time?
Good. I think the allocated 40 minutes for this, so maybe if we say.
All right, I'm going to go over a solution, which is, again, another slightly contrived solution. But in the part 3, we will be talking about how estimators are usually used in a real VQA program. So here, and the solution is kind of based on the previous exercise, during which we talk about how we would compute expectation values for the poly x and y operators in the 1 and plus states. So in my solution, I'm gonna do the same thing, but with a slight small twist. And that is, we would do a circuit in the 1 state and use the poly x operator if the expectation value, the calculated expectation value is greater than 0. And the poly y operator if it's less than 0. And because the expectation values should vanish, which means it should be approximately 0, we are going to set a target of 0.01. And we are not setting a target of 0 because the simulation is not gonna give us a perfect 50-50 chance, which means we are most likely never gonna get a 0. It'll just become an infinite loop, which is not what we want. All right, let me zoom in a little bit. So the first step, again, is to authenticate with the server. And we do that by initializing this Qiskit Runtime service class, which would return us a service instance. So here I am preparing circuit, 1 qubit circuit, and it just does an X gate on qubit 0 and the measurement. Then I am going to prepare my 2 operators. So there is the poly x and the poly y operators. And here I'm using the sparse polyop class from Qiskit, in which I can just do a from list. This is not gonna fit on the screen. Oh. All right, I should have. All right, so here I am calling the estimator primitive. So I am first opening my runtime session using the width, which gives me how I define the context manager. So I do a width estimator, passing my circuits and the possible observables I want to use, my x and y operators, the service instance that I got after authenticating with the server, and the backend. Again, I'm just gonna use the Kazan simulator. So here I'm setting my target as 0.01, and I call my initial value is from calling the estimator primitive with my circuits and the X operator. So that's my expectation value. So as long as the expectation value is, or the absolute of it, is greater than my target of 0.01, I'm gonna do this loop. And the loop just says, oh, if it's greater than 0, I'm gonna use the X operator, and if it's smaller than 0, I will use the Y operator. And then I just call my estimator repeatedly, passing in a different observable each time. So, well, I guess I can't really scroll it down, but so this is again, very contrived example of calling the estimator repeatedly within a Qiskit runtime session. All right, does anyone have any questions about Qiskit runtime or in general? If not, I think we can take 10-minute break, and we'll come back at 11. Oh, well, I guess I should mention again that the solution is in the solutions branch inside the repo.
You guys ready for the third and final part? All right. Okay, so I'm going to spend a few minutes talking about how to build on what Jessie talked about, but specifically for applications. And in particular, I'll show how you might use this for chemistry problems, combinatorial optimization problems. You can also use this for machine learning, but I did not include that specifically in this or in the exercises, but those also, in principle, can leverage this too. All right, so kind of recapping a little bit, and I think Jessie pointed this out pretty well, which is that pretty much anything that you want to do with quantum computing requires an interplay between a classical machine and the quantum machine. In some form or another, whether you're doing an iterative variational quantum algorithm or not, at the end of the day, that's usually what you're doing. You have some kind of back and forth. So the variational quantum algorithm is kind of like the main example that everyone points to for these. And these are kind of considered like the workhorse of near-term algorithms because we can run these on machines today, as opposed to what are known as fault-tolerant algorithms, which require quantum error correction and have massive overhead and require, of order millions or tens of millions of qubits and things like that. So those are clearly out of reach right now, but we can run what are called variational quantum algorithms. And the reason why we can run those is because they usually let us get away with running shorter depth circuits and then outsourcing some of the computation to classical optimizers. So you kind of pay the price in that now you have to usually optimize a very complex landscape with a classical optimizer, but the benefit is that you can run the quantum part on today's machines, usually, not always. So some common examples of where you would use these type of variational algorithms are with chemistry, so the variational quantum eigensolver, which is used for finding ground states of quantum systems. You could use it if you have binary optimization problems. You can use an algorithm called QAOA for finding good solutions, like MaxCut, for example. For machine learning, you can use this for training quantum circuits to be classifiers. You can use it for training quantum circuits to be used as quantum kernels in kernel methods for machine learning. And so in most of these cases, you can kind of think of what you're doing as you have some system represented by a Hamiltonian, and you want to minimize the energy of that Hamiltonian. And so the way you do that is you calculate expectation values. And then you can use a classical optimizer to find an approximate ground state. And so the reason why I kind of touched on this already, but the reason why these are useful is because it's usually the case that we can run these algorithms with short depth circuits that are within reach of our hardware today. And they kind of, because we're doing this sort of classical optimization, we can kind of handle some of the inherent noise on the machines a little bit. So here's a little bit more detail about what these algorithms kind of look like. So suppose you want to find the ground state of some system, which you represent with a Hamiltonian. So on the left here would be a molecule. This is lithium hydride. So maybe you want to find the ground state energy of that molecule. Or maybe you have a graph like here, like a combinatorial optimization problem, and you want to find some, whatever this graph represents, maybe it's MaxCut or something. You want to find a good approximate ground state solution. So what you can do is if you can represent your problem in terms of a Hamiltonian, then you want to calculate expectation values of that Hamiltonian, which gives you an energy. And then you want to minimize the energy using some kind of classical optimization routine. So you can use this idea of what's called the variational principle, which if you take a good guess for what the ground state wave function or solution is, which is this psi here, and maybe it has some parameters that you inject into it, then you can use that approximate ground state, or a guess, or an ansatz, sometimes it's called, to calculate expectation values of your system or your Hamiltonian. And that is guaranteed to be at least greater than or equal to the exact ground state energy. And then what you can do is you can use the quantum computer to calculate those expectation values, which we saw before, and then pass to a classical optimization routine that as a cost function and use it to update the parameters in your circuit using a classical optimizer. And you repeat this back and forth until you decide it's good enough or you reach some kind of stopping condition. And that'll give you an approximate ground state solution. So for the case of chemistry, suppose you wanted to calculate ground state energy. So we have a simple little molecule. It has some energy spectrum. Maybe you want to find what is the ground state. So what you do is you, so I'm not a chemist, disclaimer, but there's a bunch of stuff that you have to do to start with the representation of a molecule and transform it from, you know, the sort of chemist view of the molecule to a form that can be mapped onto quantum hardware. So you have to, if you're familiar with like second quantization, you have to write down your system in second quantized form, and then you have to map to qubit operators so that you can run it on a quantum computer. So there's a bunch of chemistry-specific stuff that has to happen for that transformation. But once you get to a Hamiltonian that's written in terms of qubits, then you can kind of just think of this as like a black box optimization thing where you have a cost function, which is expectation value of the Hamiltonian, and then you call a classical optimizer to update the parameters. So this little circuit here is just indicating this is my guess for what the ground state wave function is, and I'm going to add parameters into it and then use some kind of classical optimizer to update those parameters at each iteration. And hopefully at the end, this circuit will be a good representation of the ground state wave function. For the case of if you want to do combinatorial optimization, it's kind of a similar thing, except kind of the upfront stuff is a little bit different. So you have some cost function that you can write in terms of binary variables. Maybe it's max cut or traveling salesman or something. You have some kind of cost function that is a function of zeros and ones, and you want to find a good solution to that problem. So what you have to do is you have to transform bits, which are 0 and 1, to qubits, and there's a trick for doing that. And what that means is that you go from your kind of classical cost function in its normal form to an Ising, what's called an Ising Hamiltonian, which is just a Hamiltonian that's a function of poly Z operators, so it's diagonal. Then, so now you have a Hamiltonian, you do exactly the same thing as you did with the chemistry problem, where you want to come up with a good guess for the ground state wave function. You compute these expectation values. So it's kind of giving you the energy of that original problem. And you plug it into your iterative algorithm and you try to find a good ground state solution. And this is just to kind of go back again to what Jessie was talking about, that this back and forth iteration is really well suited to the Qiskit Runtime framework, because instead of having to, like every single iteration of the algorithm, you would normally have to get back into the line of the queue of the hardware and wait until something opens up and then send your next batch of circuits, get an answer, repeat. And that can be extremely slow. There's other latencies as well. So one nice thing here is that you can kind of open up a session and you can have access to that hardware during this iteration. And so it's a much more natural and nice way of running these algorithms. And then I was just going to point out currently there's a couple of so-called pre-built runtime programs that are available. One is for VQE and the other is QAOA. And so these are kind of, they're more like ready to go, kind of, so to speak. And you can just plug in your inputs and run them. But I think these were like the original versions of what Jessie was showing you now with these like estimator and sampler primitives and this idea of sessions. These were kind of like the original versions of this. And I think, Jessie, you were saying these might be moved out somewhere later.
Yeah, initially we built this pre-built program because they're easy for people to use. You can just plug in your parameters. But the issue with these is that they do not scale well classically. So I think the plan is to keep them, but move them into like a proper cloud environment, so that they can scale
Okay, so then I will switch over to some slides here, or a notebook slide. If I can find my cursor. So I'm going to show you guys how to build. It's kind of like what Jessie showed with this opening up a sampler or an estimator and doing some kind of iterative procedure. But here I'll show you how to do that using classical optimizers. So kind of a little bit more of the standard framework of a variational quantum algorithm. So I'll show you the mechanics of how to set that up. And then the exercise will be to take this as a starting point and see if you can input either a chemistry problem as the input or a combinatorial optimization problem. You guys can choose which one you want to do. But I'll show you, this is kind of the mechanics of how you set it up, and then you kind of just change what problem you want to put into it. So the sort of flow of this is you want to define a Hamiltonian that represents your system. So maybe it represents a molecule, maybe it represents a material, maybe some kind of max cut graph, something else. And then you want to pick a quantum circuit that you think will be a good guess for the ground state. And that circuit will have parameters in it that you will train to try and find the ground state. And so you set up this optimization loop between the energy of that Hamiltonian and your classical optimizer that updates the parameters in your circuit. And then at the end, you can retrieve the result, which is an approximation to the ground state. All right. Okay, so in this, it's a really, really simple example. I'm going to build a 4-qubit operator that's diagonal. So it just has 2 poly Z operators on the first 2 qubits, and then the identity on the second 2. So this will represent our Hamiltonian. It's very simple, and to pass this into the Qiskit runtime framework, we have to represent this as a sparse poly operator. Jessie showed this a little bit before too, but and then we have to turn it into a list. And so when it's in that format, then we can pass it to Qiskit runtime. And this coefficient here just means that I have one term, like the coefficient in front of my ZZII operator is just 1. Okay, so since it's a really simple Hamiltonian with one term and they're poly Z operators, you can just look at it and know that the minimum energy is -1 because of the eigenvalues of the poly Z operator. So this is what we expect to get when we run this iterative procedure. So the next thing is to pick a good guess for the ground state wave function, or ansatz. You can pick anything you want, but here I picked what's called efficient SU2, and it's just called that because it's good for the noisy quantum hardware. It gives you short depth circuits, so that's why it's called efficient SU2. But so it's composed of 2 layers of single qubit gates that are parametrized. So we have theta 0 to theta 7, and then we have a little ladder of C0 gates. And then we have another set of single qubit gates that are also parametrized. And so what this algorithm will do is we'll initialize these thetas to some random value or whatever value you care about. And then we'll use our classical optimizer to tune the values of those thetas at each iteration. And then at the end, this circuit should be a good representation of the ground state. All right, so because we're interested in the energy of this system, we'll use the estimator primitive, because the estimator lets us do expectation values of operators. And then we want to pick a classical optimizer to adjust the circuit parameters. And then we'll define a callback function, which just lets us store all the information that we get as part of the optimization process. Hopefully you guys can see that. All right, so we set up a Qiskit runtime service. Oh, so a lot of this you already saw from Jessie, but we started a Qiskit runtime service. We want to tell it what backend we want to use. So we're going to use the CHASM simulator. And then I'm going to use an optimizer that requires the following callback function structure. So it'll have, and if you're interested in this, I can link to the documentation, but it'll tell you the number of function evaluations the optimizer makes. Points is the set of circuit parameters that it gets at each iteration. Fvals is the value of the cost function at each iteration. Updates is something step size, I think. It's, how large the step size is at each iteration of the optimization, and accepted was whether whether your cost went down or not. And if it went down, that's good. Okay. Now we set up the estimator primitive. So this should look pretty similar from before. We set up an estimator. We pass it the circuit that we just built, that is our guess for the ground state. We pass in our operator, which is just that diagonal Hamiltonian. We pass it the options, which was the back end, and then the service. And then what we do is we can define a function that explicitly calculates the expectation value given an input x, which is our list of parameter values. So all that we do is this is really just like a simple wrapper where you're making a call to the estimator. You're telling it, this is my ground state ansatz, this is my Hamiltonian, and then these are the parameters that I'm going to pass to my circuit for this iteration. And then it will return the results of that for you. And then this is just the callback function, which I kind of went through before, that has the 5 different inputs, and it will store these in the history dictionary during the optimization. Okay, and then the other thing we can do is we can tell the optimizer to initialize the parameters at some value. So I'm just making them random here. So you can get from the circuit object the number of parameters in your circuit with this method num parameters. And so I'm just saying like initialize an array of random values for this circuit. And then I'm going to use an optimizer called SPSA, which is available in Qiskit. If you want to know about the details of that, we can chat about it, but maybe for now I'll skip over it. But this, the inputs to this is, right. So SPSA, the first argument is to tell it how many iterations you want it to take. So I am telling it to do this for 20 iterations, and then I'm passing it this callback function so that it stores the information for me. Okay, and once you have the optimizer set up, then I guess if you're familiar with SciPy optimizers, this would look familiar to you. We just call optimizer.minimize. You pass it the function that you're trying to minimize, which is our evaluate expectation. And then you can pass it this initial point, this x0. And then you run this cell, and it will optimize that expectation value for you. Okay, just zoom out a little. But so I'm not going to run this because it was a little slow, but I ran it for 20 iterations. If I zoom out, it got down to -1. So if you remember, that was what we expected the answer to be. So that's good. And then we can just check from our callback, our history dictionary, we can pull out the objective function values. And I'm just grabbing the last one and comparing it to the target energy. So it did what it should, which is great. And then you can also, from the callback, get other stuff. Actually, this is not from the callback. This is from the results object itself. So I can say result.x, and x will give me what the optimal set of circuit parameters were for this optimization. So these are all the parameters that are encoded into the circuit. Okay, so that was kind of all I was going to say about this. For the exercise, essentially what you would do is you would start with this kind of basic framework where you have an estimator and you tell it, you set up a classical optimizer, you pass it your objective function, and you optimize. The only difference is that instead of passing it just some really simple Hamiltonian that I did here, you can see if you can set up an operator corresponding to a chemistry problem or an optimization problem. So I will show you those quickly. So there's 2 files in the part 3, in the docs/tutorials folder. There's several files that start with part 3. The 2 exercises are the ones that say chemistry exercise and optimization exercise. So for the chemistry one, I give you some hints here. So the problem is, suppose you're given the H2 molecule, and the 2 hydrogen atoms are some distance apart. Try to find the ground state energy of that. And so this is the link to the generic VQA that I just walked you through. So you can see how to use the estimator primitive. And then if you're interested in how to set up the H2 molecule problem, there's a tutorial here from Qiskit Nature that shows you how to do it. And then I give you some suggestions for different kind of functionality that you might want to try to use. And then for the optimization problem, it's the same thing, but instead of a chemistry problem, you can set up a binary optimization problem. So I give you a few examples of things you could try. So there is the weight matrix here of a 4-node max cut. So you could start with that if you want. Or you could just start directly with this cubo that I defined with 3 binary variables. And in either case, I linked to a couple of tutorials on how to set up, if you're starting from the weight matrix or from the cubo, how you set up those problems and transform them into Hamiltonians. And then I give you a few other hints about maybe good optimizers to try and things like that. This is probably a pretty challenging exercise, I'll admit. So definitely feel free to look at it later too. And I guess you merge the solutions, right? So there's a solution for both of these in the tutorial folder. So they're just ways that I solved them, but I'm sure you could do other ways of doing it. So you can take a look at that as well. But yeah, any questions on that? No? All right. Godspeed. I guess we have, 35 minutes left, roughly. So yeah, thanks for making it all the way through, almost. Okay, so this is the file part 3 optimization exercise solution. And you can definitely take a look at these later. They're pretty long, so yeah, I'm not going to go through all this in a ton of detail, but I'll just kind of skim through some of it. So I'll show you the one where we're given this cubo, and we want to minimize this function. So what I will do, this one was maybe a little trickier because you have to use 2 primitives. You have to use the estimator to do the minimization, and then at the end, what you want to do is use the sampler to sample bit strings from that solution to get the actual answer to your optimization problem. Okay, so I'll skim down here. All right, so if you kind of scroll halfway down the solution notebook, there's one for this cubo specifically. If you guys can see that. But okay, so within the Qiskit optimization module, there's a bunch of functionality for dealing with these cubos. There's a class called the quadratic program, and that lets you, so if anyone here is familiar with DOCplex, it lets you build optimization programs in the same sort of way that you would do that with DOCplex. So here we're going to build a quadratic program, and then what we can do is we add our binary variables to that program. So here I just have 3 of them, X, Y, and Z. And then I can tell it that I want to minimize this program, and then I tell it what linear and quadratic terms I have. And so I can pass it the list of the coefficients in that original cubo minimization expression that I had at the beginning. And then I can pass it this dictionary for the quadratic, like the cross terms with their coefficients. And then you can print it out and look at it. So this is the original cubo that I specified at the beginning, and then here we're just regenerating that, but in this quadratic program format. So then once you have this, what you want to do is you want to take these binary variables and this kind of expression here, and you want to convert it into an Ising type Hamiltonian. So what that means is you take these binary variables that are 0, 1, you map them to kind of like spins, like plus and minus 1, which you can do with the poly z operator. And then you should get an expression that is a function of terms linear and quadratic in poly z operators. So the way that you do that is you can just call this to Ising method of the quadratic program, and it will give you the qubit operator, now in qubit form, and then if you have sort of like a constant shift of your Hamiltonian, it will give you that. So you can print it out. The operator here is on 3 qubits, and here's the coefficients. It's a completely diagonal operator, which it should be since we're doing a classical optimization problem in the standard way. And then so now you can kind of just think of this, like forget that it was even an optimization problem. All you have is an operator, and you want to minimize its expectation value. So here, I'll skip over this, but here I'm just solving using a NumPy minimum eigensolver. Like I'm solving exactly for the ground state, so we know what we should get. And so it's saying that the minimum objective function value is -2, and then the solution for the binary variables is 0, 1, 0. So that's kind of what we would expect to see with our quantum approach. So then what we do is we have an Ising Hamiltonian, but we have to convert it into this poly-sum-op form for Qiskit Runtime. So there's just a little like kind of pre-processing step here where we take our qubit operator and we pull out the coefficients and we plug it into this poly-sum-op object. You can look up all the details of this later, but it's just a little pre-processing, and it puts it in the right format for Qiskit Runtime. So this is just our original Hamiltonian, but slightly different format. And then all this stuff is kind of the same as what you saw before. We can set up a Qiskit Runtime service, pick a simulator. Maybe later you want to try real hardware if you have lots of time. And we can pick a circuit for our ground state. I'm going to pick real amplitudes. There's good reasons why you might want to use this, but you could try other things too. And this is what our circuit looks like. So it has 9 parameters in it. And then this is the same block of code you guys have seen several times now. So this is our callback dictionary. But we set up an estimator, pass it the circuit, the operators, all the other good stuff. We tell it, we make this little wrapper function that just does the expectation value call for us. And then we set up a classical optimizer and then minimize that function. And so if you run this, it'll take just a little bit, but you can run it, and at the end, you get a results object. So I can pull out here the final set of circuit parameters that it found. And so at this point, what you've done essentially is you've minimized the energy of that Hamiltonian, and you're given what were the set of parameters in my circuit that produces that minimum energy. But what you really want is the solution to your original QUBO problem. So these binary variables that represent your classical optimization problem. So what you can do is, since you know what these optimized circuit parameters are, you can plug them into your circuit that you set up, and then you just sample from it. And what you should find is that those samples that you get, you can say, okay, like say I measure the bit string 0, 0, 1. What is the objective function of my original problem for that set of binary variables? and you can kind of sweep over all the possible bit strings that you sampled, and you can pull out which is the one that gives you the best objective function value, and hopefully it's also the most probable. So that's where the sampler comes in, is we want to sample those bit strings. So here you have to remember to add in a measurement to your circuit, otherwise sampler won't know what to do. So you pass it your circuit with the measurement attached to the end, and like how Jessie showed, you call the sampler with your circuits. These are the optimized parameter values that our estimator found. And at the end, we get this dictionary of probabilities. And here I'm showing the convergence of the algorithm, and then on the right is a histogram of the different bit strings I sampled. So pretty much there's like a little bit on this bit string and a little bit on this one, but mostly you get 0, 1, 0, which, as you might recall, was the correct answer to this problem. But then what we can do to actually verify that is a little post-processing here. You can look at it later, but essentially all I'm doing is I'm iterating over the samples, those bit strings, and I'm plugging them into our original quadratic program and saying what is the value of my cost function for those bit strings. And then at the end, I get this list that I've sorted according to best objective function value. So you'll see the bit string 0, 1, 0 corresponds to objective function value -2 with probability 99%. And so all you want to do is you want to pick what was the best objective function value, which is this top one, so 0, 1, 0. And I can just kind of print that out, and I get it with nearly 100% probability, which is ideal. So that's kind of the main flow of it. It's the same for the weight matrix one, which I also show in this notebook. And then the chemistry one is a little bit more chemistry heavy. So if you're a chemist by chance, maybe you'll enjoy setting up that part of it. But the flow is it's pretty much the same, except no sampler at the end. All right, well, with 2 minutes to spare, should we call it a wrap? All right. I guess there's a Slack channel, so if you guys have other questions later, feel free to ping us. I don't know how long that will be up for, but